stands for reduction oxidation reaction. So reduction oxidation reaction. Okay, this is just abbreviation for reaction. RXN is an abbreviation for reaction. A redox reaction is a reaction in which one or more electrons are transferred. So it basically means like, I don't want to call them charges, but basically the electrons move around and due to the electronegativity of different atoms, right? Electrons are pulled. So one atom might be like a +2 charge in this certain compound, but when it moves around, maybe now it's a +3 charge, right? At the end of the reaction, maybe now it's a +3. And so we're going to look at how can we tell if there's been electrons transferred in the reaction and how can we tell if there's not been, right? But if there's been an electron transfer, we call it a redox reaction. Not all reactions are redox, only some. Okay, so we're going to figure out how do we know, right? And then how do we categorize them? So this is an example of sodium and chlorine, okay? The formation of sodium and chlorine. So we start with 2 sodium atoms and a chlorine molecule, right? Chlorine is do you remember what the word is? That it has to be CO2. What's that called? It is a...
It has to be what?
Okay, so chlorine is one of those elements that has to exist in a pair.
Oh, the gases?
Uh-huh. So what are those called? Do you remember the name for that? There's 7 of them. Remember, they make the 7. They're they're called diatomics. 2 atoms, right? Diatomics, 2 atoms. So chlorine is a diatomic, so it has to exist with its buddy, right? Cl2. And so in this reaction, these elements go from basically individuals to now being in a compound, right? They go from being completely fine on their own to now being part of a compound. And so this is an example of a redox reaction. There's been electron transfers that have happened in order for this formation to happen. Okay, so we're going to look at how do we know? How do we know what the electrons are being transferred? How do we know all that stuff? So we have to talk about something called oxidation states. Okay, oxidation states, or I typically call them oxidation numbers. Okay, I'll say, what's the oxidation number? Okay, rather than oxidation states, but they mean the same thing. Now, I want you to think about, I want to give a definition of what is an oxidation number. Okay, an oxidation number is basically a pseudo charge, right? It's not a full charge, but it's like almost a charge, right? It's almost a charge, not a full charge, but it's almost a charge. Okay, so an oxidation number is a pseudo charge. You know what pseudo means? It means kinda. Okay, it's a kinda charge. Okay, so it is not a full-on charge. It's like that where electrons are kind of pulling in my direction, but it's not really, right? So when we assign oxidation numbers, however, most of the time they actually do match the element's assigned charge. Most of the time they do. But I'm going to give us some rules for how do we figure out the oxidation number of an atom. Okay, the oxidation state of an atom in an element by itself, and maybe we need to add this in here, element by itself is equal to 0. Okay, so in our last example, when we had sodium plus Cl2, so 2A, this sodium is by itself. It has an oxidation state of 0. This chlorine is an element by itself, right? It's not paired with anything else. It's in its natural state, so it has an oxidation number of 0. Okay, so both of these started out with oxidation states of 0. At the end of our compound, we'll talk about what is the oxidation state here, but we know this was a redox, so there's been some sort of electron move, and we'll look at this one a little bit later, okay? But elements by itself have an oxidation state or an oxidation number of 0. Okay, the oxidation state of a monatomic ion is equal to the charge of the ion. So if we have a reaction that says H plus something, right? The oxidation state would just match the charge. The oxidation state of that hydrogen would be +1, right? It would match the charge. Okay, so if it exists as an ion, that means the electrons must be arranged so that is an ion, right? Oxidation state is basically showing us how are the electrons arranged around that particular atom. In things that are by themselves, there's nothing going on with their electrons, right? Does that kind of make sense? So if it's by itself, it's like peaceful, it's complete, it's as it's supposed to be, the electrons aren't being moved around. But if I'm an ion, that means that I've had an electron change already, right? So I have an oxidation state. All right, here are what we call the big three: hydrogen, fluorine, then oxygen and hydrogen. They go in that order. Okay, the big three here, they kind of trump everything else. So if you have fluorine in a compound, its oxidation number will always be -1. So that's the one we assign first. Okay, it kind of gets like dominance here because it's the most electronegative atom that we have, right? And so it will take electrons from anything else in a compound. So its oxidation number is -1. The next big three, I call them the big three because we always check our compounds to see, is one of the big three present? And then we can build our oxidation numbers from there, okay? Oxygen is going to be -2 in covalent compounds, except if it's in peroxide. That means when it's bonded with hydrogen, then it would be -1. Okay, and then hydrogen is +1 in all covalent compounds.
So what if you had like fluorine and oxygen like in the same? Is that
Yep.
not possible?
So you would give fluorine first, and then oxygen might have to adjust its oxidation number.
Okay.
So you make sure fluorine is correct, and then oxygen might have to adjust. And I'll show you how do we figure out if we need to adjust, right? We do a little bit with their subscript and stuff like that. We work out positives, negatives. So I'll show you that. Okay, so if I'm going to make one extra little note in here, okay? If the big three are not present, the most electronegative keeps its charge. Okay? If the big three are not present, the most electronegative keeps its charge. Now, how do we know which one's the most electronegative? It's the one that comes last. Okay, it's the one that comes last. Okay, or if you want to think about it, it's the element that's closest to fluorine. Okay, that's how we know. But we build compounds from least electronegative to most electronegative. So it's always going to come last. That one gets to keep its regular charge. So following that rule, what would be the oxidation number of, in this molecule, what would be the oxidation number of chlorine? What's chlorine's normal charge? -1, right? It would be -1. That would be the oxidation number. And see how that's different from its oxidation number originally? That's how I know it's a redox reaction, right? Chlorine started out as a 0, but after the reaction took place, now it's a -1. That's how I know it's redox. If those did not change, if it started as a 0 and ended as a 0, that means it's not a redox reaction,
So
right?
how
If
would it-
nothing in it changed.
Oh, and then at 0, like how?
So yeah, I'll show you some examples of that, of where things don't change, right? Or if it started at -1 and ended at -1, right? That could be the case too. But yes, if we see the element does not change, if no elements change, it would be not a redox reaction. Okay, in a compound, the sum of all of our oxidation numbers have to add up to 0. Okay, the sum of all of our oxidation numbers must add up to 0. So in a compound that does not have a charge, our oxidation states have to add up to 0. And if our ion or whatever it does have a charge, our oxidation states add up to that charge, whatever it is. So this is a lot of rules, and I know it seems very arbitrary for right now, but when we start seeing it in examples, I think it's going to make a difference. So let's go ahead and keep looking here at NaCl. We said chlorine is -1. Right? I like to put their oxidation numbers up at the top. That's not like a hard rule or anything, and it's not a full charge, so we're not going to assign it a full charge, but I just like to do that. I like to kind of leave the bottom space as like a workspace for me to kind of get my positives and negatives in order, but it doesn't matter, however you want to work it out. If we know that the sum of our oxidation states for our compound have to add up to 0, what does sodium have to be? +1, right? And so the oxidation state of sodium went from 0 to +1, and chlorine went from 0 to -1. So that is a redox reaction, right?
But
There has
wouldn't
been a
they,
notch.
like, balance each other and make it 0?
They do, but the individual atoms, right? We're looking at sodium individually and chlorine individually. But you are right, yes. They always should, right? Because the electrons can't disappear, right? What happens is that chlorine nabbed that electron from sodium and kind of hanging on to it within that ionic compound. Now, this compound is ionic, isn't it? Because it's a metal and a non-metal. So you will always usually see these compounds really keep their own charges because it's ionic, right? So really, a true electron transfer is happening, right? We did fully take that. So a charge and the oxidation state in this ionic compounds are the same, okay? Covalent compounds is where it gets a little bit trickier. So we'll look at those, okay? But do I have some on the next one? Ooh, goodness, they're kind of gross. Okay, let's start, let's actually start at the bottom, okay? SF4. So does it have one of our big three?
Yeah.
Yes.
It does. And we said fluorine is always a -1, right? And so I like to, I said, kind of make the bottom my workspace, right? And so if I have 4 fluorines that are each -1, that means that I've got a total of -4 happening here, right? And what did we say we wanted the total to add up to be? 0. And so what -4 must equal 0? Okay, +4. And how many sulfurs have to share that +4? Just 1, right? So that means the sulfur must have an oxidation state of +4. Okay, so then we could circle it and we could say our fluorine's oxidation number is -1, sulfur's oxidation number is +4, right? And sulfur, that's not its normal charge, is it? It likes to be -2, right? So fluorine's really hogging the electrons within this compound, right? They're shared, but they're not shared evenly. And so that's really what our oxidation state is showing us, right? How is electronegativity happening within the molecule? Okay, does that kind of make sense? I just use the bottom as kind of my workspace, right? You'll notice I multiply down and divide on the way back up. And I tend to always work like this. I kind of build this box in this direction. Okay, so let's look at our next one here. PCl5. PCl5. Now, does it have any of the big three? Nope, no fluorine, no oxygen, no hydrogen. So now our rule is the one comes last gets to keep its regular charge, which for chlorine is -1, which gives us -5, right? Because there's 5 of them. And so phosphorus has to be then a +5, right? +5. +5 and -1. That's how we would report that, okay? So this is just us assigning oxidation numbers. We would have to actually apply this to a reaction, right? And we would do this for each compound in the reaction to figure out what was phosphorus before and what is phosphorus after. And that'll tell us, is it redox or is it not? Okay. Let's look at the next one, MnO2. MnO2. Now, this is ionic, isn't it? So a little simpler to tell what our oxidation states are going to be because typically they just follow the charge. But let's work through it. Okay, this is always -2, which means -4, which means manganese needs to be +4. Okay, not too bad. Okay, let's move on to CO3 -2. This one's a little bit different. Because now we don't want our work down here to add up to 0. We want it to add up to -2, right? Because the sum of our oxidation numbers, and when we say sum of the oxidation numbers, we mean the totals, not like these guys, right? The totals of them have to add up to the charge. So let's work through from oxygen here. Oxygen is -2, and there's 3 of them, so that's -6. But we don't want it to add up to 0. We want it to add up to -2. And so what -6 equals -2? +4. And there's just 1 carbon there, so that becomes +4. So carbon is +4, oxygen is -2.
If there were 2 carbon, it would be +2.
Exactly. If there were 2 carbon here that needed to share that +4, we would like divide on our way up, so then that would be +2. Okay, let's take a look at the next one. This one's a little more complex. K2CR2O7. This is kind of a weird one, right? This is an ionic compound that contains a polyatomic ion and a metal. right? Polyatomic ion here, I think that's chromate, I would assume. I don't have my thing in front of me, but I have a metal and then a polyatomic ion. So a couple ways you could go about this. You could separate them, right? And know the metal is going to keep its charge and then do chromate on its own based on what its charge is. That's usually what I recommend, but we can do it all in one step too. We know here that we're going to start with oxygen, right? We always start with the one farthest here. Usually we work over, and then the middle guy is the one that's left to kind of maybe adjust. Okay, so we always kind of work outside and then in. Okay, that's my suggestion. Okay, so oxygen we know is -2, and there's 7 of them, so that gives me -14. Does my ionic compound here have a charge? It does not. So that means my workspace has to add up to 0. So now I'm going to jump the middle guy and know that potassium will keep its charge as its oxidation number because it's a metal. And it will just get to keep it. So +1, that gives me +2. So now 2 plus what? -14 equals 0. 12. That's okay. 12. And 2 chromiums need to share that 12. So that means chromium becomes +6. Okay, so potassium's +1, oxygen is -2. Do we see how that kind of works? Mm-hmm. If we get a big complex compound like that, you could split it into its ions, right? And know that potassium would each be a +1, and there's 2 of them, right? And then we'd left with Cr2O7, which has a -2 charge, right? We could work it like that, or you can just work outside in. That's fine. That works too. Okay. Any questions about assigning their oxidation numbers? Do you feel kind of comfortable with that? Mm-hmm. Good. Okay. It acts like a charge, but it's just not a full charge because we're really showing where are the electrons being pulled from, right? All of chromium's electrons are being pulled outward, right? They're being pulled away from them by all of those oxygens. And so that's really what we're showing. We're almost showing like the partial positive, partial negative that's happening in that polar bond. But it's not a full charge because the electrons aren't being jumped, right? They're not being transferred fully. So, okay, so now let's figure out, once we know the oxidation states, how do we know what's redox reaction? Right? In order for there to be a redox reaction, there is a transfer of electrons. Has to be a transfer of electrons. The transfer may occur to form ions, or it may occur to form not charged things, right? It might go back to its basic state. It could happen anyway. But within a redox reaction, there is an element that undergoes oxidation, and there is a separate element that undergoes reduction. That's where the nickname comes from. So one of our elements is oxidized, and one of our elements is reduced. Okay, so that's how we've got to think about that. Now, here's what I think of it. Here's the way I think of it, okay? And in an oxidation, for the element that is being oxidized, it says we have an increase of oxidation state. That's too much for me to think about, okay? The words increase in oxidation state, don't love that. But here's how I like to think about it. Increase in oxidation state means we lose our electrons. We lose electrons. So basically our charge becomes more positive, right? We're losing electrons. Reductions means we actually gain electrons, right? That seems backwards, okay? We call it reduction, but we're gaining electrons, okay? So, but it's reduction because we're decreasing our oxidation state. That's why. Okay, so here's the way I think of it. This is a really common acronym here to think about it. Oil rig. So I say oxidation is lost, reduction is gain, and then you got to tag on of electrons, right? Oxidation is loss of electrons, reduction is gain. Oil rig is a very common acronym, right? If you go take college chemistry class, you're going to hear that acronym being used for this section. Oxidation is lost, reduction is gained. So in our previous example, let's go back to here. We had 2Na plus Cl2 yields NaCl. And we said this was 0, 0, plus 1, -1. So we agree that it's redox because there's been an electron transfer, but which one is reduced and which one is oxidized? Okay, oxidation is loss of electrons. So which one lost electrons? Sodium or chlorine? Sodium. So that means sodium is oxidized, and that would mean chlorine is reduced, right? Because chlorine gained the electron. So that's really what we're looking for in a redox reaction. Is it redox? And then you have to identify which element was oxidized and which element was reduced. Now, they also call them agents, right? So if sodium is the one that is oxidized, it is the reducing agent. It is what caused chlorine's reduction. I very rarely talk about them in terms of agents, but your book will ask you a couple questions about that. So I want you to make sure you understand. If it is the one that is being oxidized, then it is automatically the reducing agent and vice versa. Okay, there might be reactions in which, like, we had a hydrogen in here somewhere. I can't even think about where I would put a hydrogen. But let's say this was attached here and there was another hydrogen over here. And hydrogen didn't change the whole time. That's fine. Okay, but if you have one that's being oxidized, there must be an element in there that's also being reduced. But you could also have extra, like spectators, right, that aren't doing anything. But you got to have one that's oxidized and one that's reduced. We can't have one that says it's oxidized and nothing being reduced, because that means our electrons disappeared somewhere, right? Or we got electrons from somewhere. So you got to make sure that you have one of each. They have to exist in a pair. Okay, so here's our agent, blah, blah, blah. I don't care about that. All right, let's try one. Which of the following are redox reactions? Okay, oxidation, reduction. That's the same as saying redox. Identify the oxidizing agent and the reducing agent. Okay, just for us to practice talking about agents. Let's look at this first one here. Zinc plus hydrochloric acid yields zinc chloride and hydrogen gas. Okay, so what do we think about the oxidation number of zinc? It's 0, right? Because it's by itself. Good. It's 0 because it's by itself. Okay, in HCl, our H is going to be plus, and our Cl is minus. Right? Our H is plus and our Cl is minus. Because hydrogen always is going to get a +1. Right? That's one of our big 3. Okay, in our next one, ZnCl2. Did this print nicer on yours? Mm-hmm. Okay, great. None of the big 3 present. So what's our rule?
So chlorine.
Exactly. Chlorine gets to keep it. And there's 2 of them. So what does zinc have to equal? +2. Right? If I needed my workspace down here, I'd say this is -2. I want it to equal 0, which means this needs to be +2, all that kind of stuff. So, and which would be 0, right? Because it's by itself. Yeah, that's a tough one, right? It's elemental at this point, right? It's by itself.
Anything that's by itself.
Exactly, because it's not going to share electrons unevenly with itself, right? So there's no tug of war happening, right? Okay, so is it redox? Did some elements change their oxidation states from reactant to product?
Yes.
They did. Okay, so it is redox for sure. Now we've got to figure out the agents, okay? It's easier for me to just figure out which one is oxidized and reduced first, and then I can talk about agents, okay? So let's figure out, remember our oxidation is lost, reduction is gained. There's our acronym. Oxidation is loss of electrons. Reduction is gain of electrons. So let's figure out here which one has been oxidized and which one has been reduced. Let's look at zinc first. Right? Zinc went from 0 to +2. So what happened to it? Zinc lost electrons. So zinc is oxidized, which means it is the what agent? The reducing agent. Okay, so zinc is oxidized, which means it is the reducing agent. And then what other ones of ours changed? Did hydrogen change?
Yeah.
It went from +1 to 0. So hydrogen what did it do? It gained electrons, which means it's been reduced, which makes it the oxidizing agent. Okay, do you see how we walked our way through that? Then what about chlorine here? Yeah, it stayed the same, right? And so it did not make a change, right? Which is fine. But we have accounted for all of the electron transfers. Let's look and see. Zinc went from 0 to +2. So it lost 2 electrons. Did hydrogen pick up those 2 electrons?
Oh, yeah. Do I just put over there?
There we go.
Yes.
It did, right? Because there were 2 hydrogens here that each went from +1 to now 0, right? So it's balancing itself, right? Zinc gave away 2 electrons, and those 2 hydrogens each picked up 1, right? They both went from +1 to 0. So we see how those 2 everything is balanced there. We're not losing electrons to nothingness, and we're not gaining them from somewhere. Okay, how do we feel about that? Kind of work through the whole thing? Okay, why don't you let's try this third one here on your own.